Welcome to the Nafems World Congress 2021. Today's presentation is using true digital twins to develop, test, and optimize complex systems. My name is Jeremy Jarrett. I'm the Executive Vice President of Kinetic Vision based in Cincinnati, Ohio. And I'd rather be with you in person in Salzburg, but I'm thrilled to present to you virtually on the power of true digital twins. Kinetic Vision is an NVIDIA-certified service delivery partner, and we help our customers digitize their physical processes across many different disciplines using technologies like modeling and simulation, virtual reality, and deep learning. Let's start with the standard definition of digital twins and how they are used today. Typically, digital twins utilize simulation models, machine learning, and statistical analysis, or the combinations thereof, with IoT sensor fusion to predict needed maintenance and minimize failure probabilities. These digital twins are typically black boxes that produce intelligent output based on the complex data they receive. True digital twins replicate all relevant aspects of the physical equivalent, including the three-dimensional environment, physics, machinery, robotics, vehicles, software systems, and even connections to external networks, and importantly, human action and interaction. So what are the advantages of using a true digital twin to develop some system or process? Well, virtual spaces and objects are much less expensive and time-consuming to create than their physical counterparts, typically 2 to 10 times. Another advantage is the creation of training data for machine learning models. Because the twin accurately represents the physical system, this data can be created synthetically. In this example, an image from a store shelf camera has a bounding box annotation depicting in-stock items. The 100 annotations in this image might cost $5 to $10 with manual labeling of each image. Now, think about the cost to label photographs of 60,000 SKUs in a typical big box retailer. The cost and time to produce synthetic equivalents is easily 10 times less. In addition, rendering synthetic training data sets is dramatically sped up with the use of GPU processing. A 100 to 500 times improvement is typical. This might be irrelevant for a single image, but consider that 10,000 images might be needed to train a model for one store section, and creating the annotated data set for an entire store easily could require millions of images. So maybe I've convinced you that developing your system or process virtually lets you innovate and optimize much faster, while at the same time dramatically cutting the overall development cost. Your next question might be, okay, I'm sold. How do I do this? One route might be the Star Trek holodeck. Well, the science isn't quite up to the holodeck yet, but we're getting closer. Today I'm presenting 3 examples that will show you the current state of the art and the power of true digital twins. An automated product inspection system, a camera-based retail AI system, and a virtual surgical suite. Here's an example of a digital twin that replicates the transport of shipments, scanning, and conveying of products in a warehouse scenario. This 3D virtual environment shows the incoming product shipments, the CT scanner, and conveying of the qualified products to production. The entire system's design, optimization, and testing was done in this virtual environment. Imagine the cost of developing this system with real machines in the shop, and the cost of idling expensive capital equipment, or even the cost to ship around a 15,000-pound CT scanner. The first benefit of this type of solution hits us immediately. We can see it working. The visualization alone affords us the opportunity to evaluate and make confident decisions in design and system setup. This means key stakeholders such as management, training, and safety teams can be involved throughout the development process, whether in a webcast or in a VR headset as shown here, and they can drop in and evaluate the system at any time. This greatly enhances team collaboration and minimizes the chance of expensive and time-consuming misunderstandings. Nothing can replace actually being there during the system development, and a true digital twin enables that. But the look of the scene is only the start. What drives that movement and behavior can be even more complex. For instance, the external robotic simulation software drives the robot's motion. Integrating the actual control methods ensures that the performance is accurate and reliable while avoiding costly commissioning of the system. It also means that the changes or testing done by the robotics team can be instantly evaluated and understood by the rest of the team. Flexibility means that you can explore and fail with little to no consequences. The team evaluated multiple design configurations of the robots, tested line speeds, and integrated machine learning vision systems to identify product stability, and human safeguards. We can even adjust the whole system to work with entirely new and different products. Okay, now let's turn to our second example of true digital twins, a camera-based retail AI system. The power of a true digital twin is in understanding not just what objects are on the shelf, but how human interaction affects them. Having a true digital twin that can be used to predict stockouts, give facings analysis, and provide other marketing data for retailers and manufacturers is invaluable. In this example, a retail AI system is being developed with the goal of using in-store cameras to monitor and detect shopper product selections. The project goals included the creation of synthetic training data, training the deep learning models, and then testing the model performance using real shopper behavior. First, the synthetic training data for the AI model is created using the virtual environment. The dataset consisted of 20,000 segmented product images using both photorealistic and domain randomized data in a 50-50 split. Domain randomization simply refers to randomizing all of the elements except the one that you want the model to identify. There are many tools that can be used to generate the synthetic images. Traditional CGI rendering software, AAA game engines, as well as physics-based simulation engines can be used to generate your data. There are also several new software tools that are designed specifically for the configuration and generation of synthetic training datasets. Using domain randomization, the machine learns to recognize products in an extreme number of environments, introducing so much noise that the algorithm has to focus only on the necessary product features. Data labeling also occurs simultaneously, which provides all of the data needed for model training in one shot. Due to the hardware acceleration of GPU technology, millions of labeled images can be synthetically created in a matter of a day or two versus the weeks or months needed for physical production and manual labeling. Once the AI model is trained, it's time for virtual shopping. Here, an avatar driven by concurrent motion capture shops in the virtual store. The human actor wears a VR headset and sees the room, the products, the cart, and even her hands and body exactly as in real life. The in-store camera is also replicated as its location and functional parameters are part of this study. The machine learning model can be tested in the digital twin using live or pre-recorded avatar motion. This is useful for ad hoc testing or more structured and automated QA testing of the system. To demonstrate the model's perception of the digital twin and the real world, we show the actual video of the test shopper on the right. As you can see, the model performs reliably in both scenarios, except for one thing. Watch the cereal boxes as they were placed in the cart. The AI model's performance is very good until the products are placed in the cart, where detection fails. It's important to note, however, that the twins behave similarly, and the virtual system mimics the physical outcomes. In hindsight, in-cart detection failed because no images of carts or products in carts were included in the deep learning training set. An additional 10,000 images were generated to include the cart in random locations with random products in it, and the model training was continued with this new information. The model can now reliably detect products placed in the cart. To summarize, A three-step process was utilized within a digital twin to train, test, and optimize the retail AI system. First, a synthetic training data set was created and used to train the deep learning model. Next, a virtual shopper avatar, driven by concurrent motion capture, selected products and placed them in her cart. And then finally, the trained model was tested on real and virtual data and optimized. Most importantly, the digital twin closely mimicked the physical system performance. A system deficiency was discovered, but it would have never reached the physical testing, as it would have been identified and remedied within the digital twin. One of the other benefits of a true digital twin is that it can be repurposed or reconfigured to assist with analysis and decision-making in multiple environments. Again, we are using a similarly trained object detection model for a distribution center and utilizing the synthetic data to help assess production metrics. As you can see, the results achieved in our production environment on the right are equivalent to the digital twin that was used for the entire development of this model. From production inspection to retail AI systems, you're now getting the sense of the power of true digital twins. Let's move to our last example, a virtual surgical suite. So for this next example, we had some secret admirers. A local news team came out to see what we're doing. Let's take a look at the clip.
Evendale-based Kinetic Vision gave WCPO 9 News reporter Lisa Smith a sneak peek at how a virtual operating room could hold the secret to medical breakthroughs.
It's not your typical operating room.
This is our virtual operating room, and it uses two really great technologies, motion capture and virtual reality combined.
Kinetic Vision and Evendale spent the last few months developing the technology needed to transport researchers, doctors, and developers of medical devices into a virtual medical setting.
This is a similar technology that you might see in making video games or for Hollywood movies and digital effects. What we're doing here is bringing that technology to training people and testing products. In this example, a new surgical suite is being developed, including room configuration, equipment layout, and new device concepts, and new procedures that are being evaluated. The surgeon avatars are driven in real time using concurrent motion capture, allowing true subject matter experts to be present inside the digital twin. The subject matter experts, in this case a surgeon and industrial designer evaluating a new procedure, experience the twin through virtual reality. They feel just like they're in the actual space. Their motion, including hands and figures, is tracked in real time, as is the position of all objects in the scene: the patient, the equipment, the tables, and the medical devices. And importantly, the scene is aware of them and can react to their presence with physics and simulated vision systems. The new devices can be evaluated virtually. They just need to feel and act like the proposed device, but complex functionality can be done digitally. A simplified 3D printed model with a spring-loaded handle can digitally replicate a prototype that would take many months and substantial cost to create. Device design iterations take hours or days instead of weeks or months, and the subject matter experts can be located anywhere in the world. Here is a composite of the surgeon headset views, motion capture process, and digital twin third-person camera. Room configuration, equipment layout, procedures, and devices are tested virtually, allowing for iteration and innovation to occur at a much faster pace. Although not shown here, it's even possible to simulate complex interactions and soft body tissue physics for in-depth evaluation of device performance during the procedure. So how far do we go with true digital twins? As any system increases in complexity, the more it costs to set up, improve, and maintain that system. Complex and overlapping systems create dependencies hidden while viewing any single aspect. Even if it is modeled and replicated perfectly, interconnected problems mean interconnected solutions. Exposing these dependencies can greatly affect success. Once we create the true digital twin, the benefits are substantial. We can effectively replicate 3D environments, functioning machines, robots, and devices, and the software to control them. We can train and test machine learning systems, and have real humans accurately interact with our virtual world in real time. The relative ease of creating virtual reality instead of a physical one empowers accelerated innovation and optimization, which dramatically decrease development time and improve stakeholder collaboration. We haven't achieved the Star Trek holodeck yet, but it's getting closer. In closing, a true digital twin gives you the early insights to avoid complex system issues and to optimize the results. Please don't hesitate to reach out with any questions. There are several more in-depth presentations on these techniques on our YouTube channel. And thank you for attending my presentation today.